So, and bioimaging in particular, it's okay. Is there a pointer or something? Did you check the pointer? Okay, not exactly. So, you see, bioimaging, very important. Molecular targeting, drug delivery, genetic engineering, biosensing, tissue engineering, photomedicine, cancer. This is just a few. It's not the exhaustive list. And as you can see, ek ke baad ek, everything is extremely important. It's changing the landscape of healthcare. Then we have 2D quantum materials and sensor devices. So I'm sure many faculty members here, the chemistry actually was looking at the profile. Some of you are working on 3D materials also. They are very important. As a matter of fact, I may dare say that any material which is actually two-dimensional in nature is actually a quantum material. And you just need to find the right application and take it to the next level, the level of product. Because usually what we do here in India, we fabricate a material, we publish one Q1 or Q2 paper, we feel very happy and the story ends. But the story cannot end. The story has to go to the next level. Okay, and then you have to present in quantum magnetic sensing. This is another area where I would just try to put a little bit spotlight, something that we are working on in our lab. And then there are quantum materials which are specifically designed for agricultural purpose. The things which are designed for optoelectronics. Optoelectronics is a conjunction of optics and electronics. It's a very, very hot area. And you have this whole new world of quantum tunneling based nano electromechanical systems for biomedical applications. So now electromechanical systems, as the word suggests, is a conjunction of electronics and mechanics. So it's like NEMS or MEMS if you want. MEMS was micro, NEMS is nano. So imagine a nanoscale cantilever. You're picking some tissue using a nanoscale cantilever. The cantilever goes, it's delivered inside, but it goes and it picks up something or injects something with nanoscale precision. So all those things get activated when you're in the quantum region. Okay. So enough of motivation for. Okay. So and this is one slide that I just told you. So quantum dots are typically sized between 1 to 10 nanometer and consist of. There are different types of quantum dots. Often they consist of group 2, 6 and or group 3, 5 elements. They exhibit very unique optical, physiochemical, electronic properties. And the one property that is very, very insanely used in biotechnological applications is the property where they actually fluoresce. Fluorescence is a very beautiful property under specific light. Fluorescence is a property where when we shine light on something, it absorbs that light and re-emits that light in a different wavelength, but often it is in the optical range. So you can see that light. So suppose it's absorbing IR, but it's emitting yellow light. Good for us, right? So because you can see, and particularly imagine if it is targeted activation, like there is a cancerous site, that cancerous site only is emitting light. That means you exactly know where all the cancer is spread. And this is so insanely good that actually it can be done in vivo also. Like as you know, there are two types of testing, in vivo and in vitro. So both are possible. So this is so good. And with very minimal toxicological component. I'm not going to go into toxicology, but please be aware, any good research comes with a price. And often the price in chemistry, the chemistry pays the toxicology part. So, and that's something we cannot wish away. We have to handle that part. So I'm not going to talk about that part because that's another area altogether. So I will skip this slide. So now let's get to some applications. And I'll try to be a little bit fast here. Because there's no point in showing you slide after slide with a lot of data and all that. Let us go try to go somewhere else. Okay. So, but I have to show something. So let us show something here. So, there are many applications of quantum dots and focusing on quantum holidays after 12th holidays. And madam, am I right that there are many faculty members who are fabricating quantum dots, right? They're experts in quantum dots. Okay. So, compared to traditional organic dyes, quantum dots are extremely superior for bioimaging applications. And they're extremely resilient to degradation. They have extreme photostability. Photostability is how quickly they degrade under exposure to light. And and they have very broad excitation and very narrow emission spectra. These are very important. Narrow emission spectra is important. Broad absorption spectra is also important. And These are some of the properties that makes it extremely superior to traditional technology. And the signal to noise ratio is extremely good. So noise is something typically something that you don't want. Even without getting into the technicalities, I can make it very technical, not required. Noise, as the word says, is noise. Whenever you have a signal, you also have a noise. That is very clear. You just take an amplifier and you turn on somebody's. Have you seen that comes from the background? That is undesirable. That's noise. And obviously, some of the cutting-edge telephones that you use, particularly iPhones, they have this insane noise cancellation algorithm that's built into the phone. So you may have seen that even when you are talking in the middle of a congested road, the person you are talking to doesn't hear the noise in the background. He just hears your voice. How is it possible? Whereas in a Mamuli phone, you will hear the honking and all that sound will come. So ever thought about how it happens? So there's a noise cancellation algorithm that's working in that phone, right? So it actually, part of it is done by machine learning also. It actually quickly picks up what is your voice that is to be carried and what is noise. Once the decision is made, it just brutally chops up all the noise and sends only the signal part. So anything which is high signal to noise ratio is desirable. And this is insane. Like you see, like I've put some number here. This is typical numbers are 10 to the power 8 times superior, 10 to the power 10 times superior. Like this is extremely good. And there are 10 to the 20 times superior to normal, 10 to the power 20 times. That basically means that a single cell which is absorbed that in fluorescent mode, you can literally pick it up even in the presence of a background. You want to create a dark environment. It's so bright, everything so brightly. Okay, so and there are some cadmium-free and quantum dots have been fabricated. So which is very big because you are also worried about toxicology. There was many technology that was working around cadmium-based quantum dots, and I think I saw some people here, faculty members have also worked in that area. So it's a very big area where you can move away from toxic materials into non-toxic materials, and particularly cadmium-free quantum dots like AgInS2 and CuInS2. So they exhibit extremely low toxicity and near infrared emission capability. These are some of the important parameters that are presently being pursued even at the VTU level. Okay, so now I go to the next application area, in vitro bioimaging with quantum dots. So this is in vitro versus in vivo. As I told you, one is in the lab and one is directly on the person with the cancer or with the. So here also quantum dots plays a very pivotal role, and it's used for cellular imaging and drug delivery. So drug delivery is important. All of you know that suppose there is a cancerous cell or there is a poisonous something which has to be targeted delivery has to be done. If you can mark that cell, let the students leave if they want to leave. It's a free word. Can't force them to listen if you want to. So targeted delivery is extremely important because I think you are aware that in cancer therapy, it is the dose which is very important, and often the high dose of the therapy kills the patient. Before cancer kills the patient, I think you are pretty much aware of this. It is the therapy which kills the patient, right? And why does it happen? Because you don't have targeted delivery. It simply goes and neutralizes everything inside the body and the person suffers. This is extremely important. Because I have just dedicated one single slide to this, I cannot emphasize how important this is and how it will alter the landscape of the country if you can own this space. So I will not get into too much of technicality, I'll just move on. So quantum dots used for bioimaging is a very hot area. And you can also target molecules, like molecular level targeting is also possible. Like first I was talking about some lump which is pretty big. Now I'm going to the next level of microscopy, which is like molecules, so targeting molecules. And this is done with much more sophistication, and chemist people here will be much more qualified to comment about how these things are done. So they are conjugated with certain antibodies and ligands, and then the docking happens, and then the targeting, the molecule is basically picked up in the background of lot many other molecules. You can pick up one specific molecule. This is like apex technology in chemistry, like how you do all these things. And okay, so let's move on. And so obviously goes without saying why you are doing all this thing, because you want to do targeted drug delivery, right? So because you want the drug to go exactly and deliver the dose at the desired spot. And So obviously, and this technology has been around at least for the last 15 years, but even though it has not come to the mainstream yet. So it will only come to the mainstream where, and particularly in India, it has not come to the mainstream. Mainstream only happens when you own the technology. Anything that is dependent on critical foreign technology to come in, there will be that one hospital in entire India, like Tata Memorial Hospital, there will be one wing, yahan pe ye hota hai. Like you have to pay a lot of money and go there. So that way, you cannot own that. You have to own the technology, the entire ecosystem you have to own. Like mining the mineral, some chemist will do the stuff, somebody will do everything, and the hospital will deliver that. Once you do that, then the cost comes out, right? So this is the goal of the National Quantum Mission. So, okay, so obviously if you have done so good as to do molecular level delivery, it goes without saying that you can use it for gene technology also. So genetic modification, genetic level engineering is also possible. And it is indeed playing a very, very hot area. As a matter of fact, this was one of the reasons why this area where people have been working has been repeatedly being nominated for the Nobel Prize. So, and very soon I will not be surprised if some of the important players here actually get Nobel Prize. So it is such a hot area because it is both straddling to both the world of chemistry and therapy, like gene therapy. Even though there are many people who don't like gene therapy, saying that we should not fiddle with nature, and that's another philosophical area, let's not get there. Okay. So now, the next slide is about multimodal imaging. Just a quick word on what is multimodal imaging. So there is some conventional imaging which is probably working for you. You don't need some very, but if you can infuse a little bit of quantum technology in conjunction with that existing technology, then it goes to the next level, right? And that is called multimodal, because you are not using one mode, you are using multiple modes to track down a particular disease or detect some problem. And that multimodal imaging is really next level with quantum technology. Because the good news is that whatever classical technologies have can coexist with quantum technology. Like quantum technology can an add-on, like it gives you extra depth. Suppose in classical technology, you identify that okay, the cancer is here, let's say in the lungs somewhere. You have identified it. You don't need quantum tech. But with quantum technology, you can actually have this microscopic targeting, as I was telling you in the last slides, where to put that. That is some very difficult decision which the doctor has to take. How much dose has to be given here and how much has to be given there, so that only the cancerous cell dies and everything else survives. The person is alive, right? And so there are many concept compounds here which are very, very hot here, very, very exciting materials which are being used. So typically quantum dots are often conjugated with MRI. MRI is a very old technology. As you know, MRI is called magnetic resonance imaging. I am not going to get into the physics of MRI, but it's a very powerful technique. So if you can use all this stuff that I was talking about, like putting quantum dots and doing this targeted picturization using MRI, MRI actually goes to the next level. Okay, so again one quick slide on in vivo imaging. In vivo bioimaging is the ultimate level in any sort of therapy, because in vivo means the cancer patient or whoever is the patient, but not just a cancer. The patient can just walk in, sit in a chair or just lie down, and the therapy is done. You're not injecting needles, you're not drawing blood, you're come after 3 days, nothing like that. You just walk in and your therapy happens. So this is in vivo bioimaging is a very, very hot area, and India wants to get into this area also. So it's possible. So we can do that. But then particularly quantum dots are the precursors with which we can do this also. Extremely high spatial resolution. Just to give you an idea of what sort of spatial resolution I am talking of, the quantum game starts with nanometer resolution. Anything which is less than nanometer resolution is not even quantum. Okay. So nanometer resolution to angstrom level resolution you can get with quantum imaging. Just imagine the precision. And temporal resolution is also very high. Typical temporal resolution that you get in quantum technology is picosecond. Suppose you have a time-stamped photography of every picosecond, that quantum technology can very easily offer you information. Time-stamps. That picosecond is 10 to the power minus 12. Nanosecond is 10 to the power minus 9. So the typical method to this photography happens is something called BRET. It's called bioluminescence resonance energy transfer. There are two technologies here at play. One is called FRET and another is called BRET. So I'll just put a little bit on that in the next slide. So it is excited via two techniques. Both of them are very common, and the physical understanding of these mechanisms are pretty good. But it is what we are stuck in is not that we don't understand the process, how to fabricate this thing and do the actual products. That is where we are stuck. So FRET is called Foster Resonance Energy Transfer, and BRET is called Bioluminescence Resonant Energy Transfer. And they are very commonly used for extremely superior imaging technology. In Foster Resonance Energy Transfer, the quantum dot itself serves as a acceptor, energy acceptor from a light emitting donor molecule. Whereas in BRET, the quantum dots accept energy from a bioluminescent enzyme. So, and often in some technologies, you can work both of them make to work in tandem. These are very high sounding words, but actually it's very easy. Just sit down and it's nothing. Concept is very straightforward. Okay, so there are some other technologies also. I don't know how to pronounce this. PE guided fluoresce. I think my pronunciation is correct, right? So these are actually quantum dots which are coated with polyethylene glycol, and they are very, very popular these days in therapeutic landscape because they have much longer circulation times. I mean, before the system ejects those quantum dots, it circulates for much longer, which has much higher application. And then you have cadmium telluride, selenide, cadmium sulfide based configurations, quantum dots also. Some of them are extremely poisonous, by the way, let me tell you, extremely toxic. I'm just not focusing on the toxic part, which facilitates near infrared imaging, and it has tremendous application. And now I will go a little bit fast. And so it is also in cancer imaging also. You can target cancer cells, insights into tumor characteristics. It can actually tell you what specific treatment also you have to engineer. Everything is possible. And it is so good that imaging of cancer cell motility and metastasis is enhanced. Metastasis is the condition, but the cancer, you can actually picturize with this technology how the cancer cell is progressing in the body. Can you understand how brutal this technology is? That is called metastasis, which the cancer develops in one part of the body and then spreads to every other part. So when a person is in metastasis, you cannot tell, it's so bad though that the cancer is spread everywhere. And typically, the way you check that is by tracking how it is progressing, and the doctor tries to find out the pathway through which it's progressing and then cuts off the pathways and then breaks it into small clumps and then does targeted treatment. So it's very important to picturize how the cell is propagating, the cancer cell is propagating. And that sort of insane technology is under the quantum. It allows you to picturize the cell propagating through the body. Okay. So also it goes for lymph node and okay, so I will skip this part. Like whatever you can think of is possible in summary. Stem cell imaging also possible. Okay, so now this also has tremendous application in biosensing, tissue engineering, and non-biological systems also. So basically, if you have an implant, that also quantum dots can help you to tell what is the right implant and what is the way in which you have to put the implant. Everything is possible. Okay, so now I will skip and jump to the next broad area. One broad area I tried to cover under, which I roughly thought as quantum dots enabled biotechnological applications. And this is running in my mind because I was trying to actually apply for the proposal, quantum biotechnology. I was very honest. So, दिमाग में बहुत कुछ चल रहा था. I thought why not reflect some of it in a talk, 10 minutes. Okay, so now another broad area where I'm aware that many of the faculty members here are working on, these are 2D materials, quantum materials, and the sensor devices. So this is some insane quantum technology. So it goes without saying that I will not get into the physics part of it. So, but if you are able to synthesize something which is actually 2D, like graphene, and there are so many others, actually you're already in the quantum realm. You don't need to know any physics for that, but that's a hard reality. Because there are many things in physics which are singularly happening only when you go to lower dimensions, right? So, and okay, so if I want to summarize the next few slides in just 1 or 2 lines, I would say only this: that because some of the peculiar properties that are emergent properties that you get only in the applications, there are a lot of technology that gets activated only when you go to these low dimensional systems. Let's say graphene, my very favorite theme, but I have a patent also. So the thing is, I just tell you in one line what are the peculiar things that happens when you look at a 2D material like graphene. So graphene, you have, you know, if you look at the electronic spectrum, how do you, when you study conduction band, electron valence band in class 11, 12, how was it taught to you? Two flat lines, right? Conduction band, electron band. Electrons are sitting in conduction band, holes are sitting in band. That's the diagram you use. Okay, turns out the diagram in the EK diagram, energy versus momentum or wave vector. If you look at the conduction band and valence band, they are actually like these cone-shaped structures, and they are actually called the Dirac cones. So, and just because of that one property, that the conduction band and the valence band are touching each other at certain points, you actually get gapless excitations. If you can push, if you want to push an electron from the valence band to the conduction band, at those 4 points, it happens without any energy. In normal semiconductor, you need to have that band gap energy has to be provided to push the electron. Right? You need the band gap energy to push the electron. Typically, that energy comes from temperature. Am I right? Thermal excitation is called. That's why you studied that number of electrons is always equal to number of holes. Because when one electron jumped from valence band to conduction band, it left a hole behind it. All these things you have studied. But now you have a scenario where the electrons are smoothly going from valence band to conduction band without any excitation energy. So even at 0 temperature, this excitation is possible. Am I making sense? You don't need temperature. Just a tiny micro nano volt bias is enough to push the electron. Right? Can you sense what are the possibilities of this sort of technology? Okay. There's a lot of technicality here, and I'm really conscious not to talk too much of technical terms here. So some of the typical techniques that are used are called surface plasmon resonance, SPR. Basically, there's a change in the refractive index of the material when certain molecules bind to certain sites, and it is so sensitive to the refractive index is so dramatic change happens to that you can easily pick up that change by passing light. How do you figure out that refractive index has changed? Just think about it. What is refractive index? Refractive index is nothing but tells you how the velocity of light is getting affected when it is going through a medium, right?
Yeah.
So if you pass light and if you have a phase sensitive measurement, again this phase sensitive apparatus we are setting up at BTU and also at RD College. So anything which is phase sensitive, if even a microscopic change in the velocity of light happens, and why will the velocity of light change? Because you have changed the refractive index. And how you change the refractive index? By attaching some particular molecule to a certain site, right? So that will be detected, and that phase change will be showing up in an interference. Let's say a Michelson interference experiment or a Mach-Zehnder interference. I'm not going to get, these are some of the typical interference geometries, if you wish. So even a tiny change of a few nanosecond delay in the propagation of light will reflect in a shift in the dark and bright spots on the screen. Right? So this is the idea. So even though this is hidden behind a lot of technical jargon, basic idea is this. Okay, so it has tremendous applications, goes without saying, in analytical chemistry and sensor development. You name any cutting edge sensor, there will be some quantum technology sitting behind it. Gas sensors. There's a huge market for gas sensors. Like in our college, we have something called experiential learning, and every year I'm tired of talking to a number of people who work on gas sensors. But the tragedy is that most of them go to SP Code and buy something cheap, they can't pay for marks and all that. So that's a travesty of our education system. But ideally, what we want to do is to build a product, not buy it from SP Code, which is typically a Chinese product. So gas detection again in a nutshell, because too much of jargon is involved. Why is it so sensitive to gas? Let's try to understand what is happening here. So again, same thing, right? The quantum technology is so sensitive. It's like, as I told you, parts per billion is nothing. Parts per billion technology you can do with classical technology only. So the quantum game starts beyond parts per billion. There's suppose one huge field, just imagine a vast football field. Just imagine, it's an experimental chamber. And in that you have put 2 molecules of some deadly toxic gas, okay? Just 2. It will detect. You have to just run the optical scan for long enough, right? So you have to allow that ray which is propagating to hit that particular thing. That's it. It will pick up. No problem. Because it's, if you think of it, quantum technology works at the atomic level. So one single atom, it strikes, and that atom goes to some internal excitation from some lower state to some higher state. The phase of the light will change. That will get reflected in some phase change in the overall thing. It's so sensitive. Okay, so gas detection. By the way, gas sensors, there's a faculty in our college who is doing very good work on that. I'm not going to take his name, doesn't matter. He's in chemical engineering department. So I was not aware. It's like $1 trillion economy, that gas sensing. I somehow gas sensing like gas. Like, okay, this much gas. No, so very big. It's a stimulus applications, and that's why quantum materials rule. Like they are the undisputed emperors of gas applications. And then you have this electrochemical and optical biosensors. So quantum materials are extremely superior again because the surface area in quantum materials, whenever you reduce the size of something, broadly speaking, you increase the surface to volume ratio. Just think about it. Take R1 and R2, where R1 is greater than R2, and calculate the surface to volume ratio. Surface is 4 pi r square, volume is 4/3 pi r. And you will figure out that as you reduce the radius, the surface to volume ratio is increasing. And that is good for any detection which is surface dominated stuff. That is good for detection. And that's why quantum technology is so good. It's simple words. Okay, and obviously electrochemical processes benefit tremendously from that. And one particular material which has been doing the very hot of these days, and I think some people in this faculty members in CMRT also work with, MZs are extremely popular. They have tremendous advantages. People are saying this ultimate dream material also for so many applications. And so, photo detectors and all these things that I'm going to show for the next few slides are stuff that our students in RG are already working on. So I will obviously not bore you with the diagrams and all this stuff. I'll just highlight what are possibilities. So photo detectors using quantum materials. So photo detector, what is the job of a photo detector? I think you can see just from the word, it should detect a photon. And if it can detect one single photon, it's quantum technology. Do you know of any technology that can detect one single photon? Like Alan Aspect, whose name I took at the beginning of the talk, he got Nobel Prize because way back in the 90s, mid-90s, he was telling, I will create photons and make them do whatever I want. Okay, he was planning also for gymnastics with photons. People thought he was crazy. But with that technology, they were able to prove something called the Bell inequality. So the Bell inequality is basically some inequalities that a person called John Bell, long back, he proposed to prove or disprove the EPR paradox. How many of you know the EPR paradox? Have you heard about EPR before? No? EPR is an acronym for Einstein, Podolsky and Rosen. Three guys. Einstein was never comfortable with quantum. Somehow he thought there's some jhol somewhere, something hidden is going on. Actually, he proposed something called the hidden variable theory. There's some hidden which we don't know. If only we knew those variables, no, there's nothing uncertain about quantum. He didn't like the fact there's uncertain principle. How the hell can something be uncertain? Everything has to be certain. This was Einstein's premise. Okay. And he was so uncomfortable that he went to the limit of proposing of some hidden variables theory. It's just that we don't know those hidden variables. If we knew those hidden variables, it's like classical physics all over. So then he was so confident of his ideas that three guys, Einstein, Podolsky, and Rosen, got together and they proposed that certain paradoxes. So these are the paradoxes. I'm not going to technicalities because today I'm deliberately wanted to stay away from all that. So they said that these paradoxes will be there if what you quantum mechanics is true. So quantum mechanics cannot be true. That was the whole conjecture. And then this smart guy called John Bell, he had a lot of respect for Einstein, but he was not doing this hero worship. Okay, he was a true scientist. So he said, okay, if Einstein is true, let us try to make it more like a quantitative statement. So he proposed this inequalities. But the only problem with this inequalities, right, you have to have some apex quantum technology. We are talking single photons, entanglements of photons and stuff like that. Who will do the technology in the 1950s? It was not even there. 40 years down the line, I am telling this deliberately because science comes at a cost. The cost is patience. You have to give the time. You cannot expect overnight returns. Now I see too many administrators coming to too many colleges. I don't take names because it will become personal. They are leading these institutes. They say, publish 10 papers. And as you pay publishing 10 papers per year, it will become China. Well, China is China because it has been doing the right thing from 1980s. And we suddenly woke up somewhere, like I don't know where, because I don't want to be political people. The point is, everything is patience. Okay? Patience का हर है. This is like for 40 years down the line, the technology that could be used to even make those measurements got enabled. Are you understanding? And 30 years down the line, that kind of work. So what are we talking about? 40% connections. This is how science operates. If you don't have the vision, if you are close to the short sighted that I want results, I want 10 papers by next year, otherwise publish or perish. ऐसा नहीं है. Okay, so he made those conjectures, those Bell inequalities, and the guy who's the famous guy, Alan Aspect and Anthony Zellinger and all that, they performed the first experiments which actually showed that this Bell inequality is being violated, which basically means that Einstein was wrong. Just to summarize what's happening, Einstein was wrong. Okay, so we are back to single photons. So I gave you one example from quantum technology, Bell inequality. Probably you're not even bothered about. After this talk, you'll forget. Now let me give you something which is much more important to you, and something that we are working in our lab. It's called an SNSPD, superconducting nanowire single photon detector. Why do you need it? Okay, you need it because it is important, one of the integral components for quantum cryptography. Quantum cryptography, why do you need? It is liquid for quantum key distribution. Why do you need quantum key distribution? Because it is an apex technology for security. Like whatever we propagate to satellites, the satellite communication that we do, we use some primitive technology, right? Some RSA technologies. Well, when I say primitive, I'm not saying it derogatory. I'm saying it's an old technology. And turns out that with quantum computers, and right now Google has built Willow, and IBM, they have also had their own technology and all that. By the way, all these IBM quantum generations are named after birds. They are called falcon, heron, all those eagle. Like the more exotic the name, the higher the technology. Okay. And the point is that quantum computers, the claim is, and it's not claim, it's actually a demonstrable fact. Google and all these companies have actually demonstrated quantum superiority. There's some debate over the problems that they selected. Apparently, the problems that they selected to show quantum superiority were tailor-made for quantum. Some of the problems are tailor-made for quantum. You can never win. It's like that Sholega Sikka. Both sides is like dead. Okay. Whatever you do. So it's like that. So there are some optimization problems that no way classical can win with quantum. Apparently, they were biased. They selected those type of problems. But so what? A problem that a classical computer can solve in a septillion years, if a machine is cracking in 5 minutes, you have to bow your head to that now. So that technology is coming. So let me cut the long story short. With quantum computers, all that RSA with which you do banking and net banking and transfer millions of rupees, no, that is gone. That is dead technology. You can crack it in a fraction of a second, 1 millionth of a second. It will be cracked. So all the present banking infrastructure, which basically rules the world and global policy, gone. So hence this scrambling, mad scrambling for quantum cryptography. If you forget everything else, at least this much you remember, we have to be there. A country of India's size, we have to own the technology. So, how do you do that? It needs you to send photons and detect photons with 100% accuracy. And when I say photons, it's not just the, oh, one light has come, oh, great. No, you have to detect the polarization state of a photon. Because the resource that the photon is carrying with it is the polarization state. Depending on the polarization state, you can the information is coded to the polarization state. Am I making sense? Every bit is 0 or 1, this much you know, right? What is the 0 or 1 for a photon? Tell me. It's a polarization state. So your state-of-the-art game when you talk of photonics is how to manipulate the polarization state, right? And how to detect that. And typically one photon has to be detected. Right now in this room, can you guess how many photons are there? Like, it's a very weird question to ask, even I don't know the answer. Just to give you some idea of numbers, otherwise I should not ask this question. Roughly, how many photons are we surrounded by right now? Is it 10 to the power 9, 10 to the power 12, or 10 to the power 23? Like, just let me see. Give you some sense of numbers. Okay, it's a hard question. You can take your time. It's a brutal number. Okay, you can't even, it's so big. And in that background, I want to think of the possibility of a single photon being emitted and detected. That is apex quantum technology. So for that technology, you need superconducting nanowire single photon detector. And for that also you need quantum mechanics. End of story. I think I've motivated you extremely well. Okay, so these are some of the materials that you can use for photon detectors. And this is a very hot area, let me put it this way. And how to give you an idea of how hot, I'm not doing self-propaganda advertisement, but this is just to sensitize you about this. This is Indian company called Cube.ai. How many of you have heard of this company? Cube.ai is the first Indian company which is claimed to build a quantum computer. Nobody has heard? Okay, so 4 of my 4th semester electronics students are interning in their lab. How can a 4th semester student be interning? Interning is not like they're learning something, they're actually developing stuff and all that. Because it's such a hot area and things are moving so fast that even students who are really good, and these students are really good, they're about with me setting up my lab and all that. So that is a possibility that stands in front of you. Because once we own that thing, everything is going to move rapidly into that new technology. We just don't have too many trained people in there. And obviously there's a lot of material at work. I'll be very honest, madam. The work that we do, we buy the materials. We cannot even think of making the material and doing our work. Because our rush is to sort of, oh, we know that quantum. How do we prove that I know quantum? Buy some material, do the work and do it. Like we are not even thinking of building the material. So I again thanking madam for giving this opportunity. Because this is the cycle should begin from making the component in your lab, if not extracting from the mine. So let's say somewhere in Jharkhand, you mine it, and then that's how country should operate and think. Okay, so as you can guess, I put one slide on this superconducting quantum magnetic sensing. I am pretty sure you have heard this word called squid. Anybody heard the word squid? When I say squid, do you think of that animal squid or something else comes to your mind? If you think of the animal squid, this is not the right place for you. I'm talking about this device called squid. Anybody has seen the device? Superconducting quantum indifference device. No? So it's very simple, topology is very simple, and the tragedy of India is that we don't have nanolithography. I'm speaking to all of you with a lot of pain. I'm hiding behind a fake smile here. Like if you find to why is India not Atmanirbhar? That story was so brutal and so sad, no? That actually you will go into some state of depression. Like actually, I'm not kidding you. Like if you make a list of what are the things you don't have, it's so big. Like lithography. What is lithography? You can etch something at nanoscale or let's say microscale precision. Tell me one college in entire VTU which is lithography facility. Well, me. Tell me one college in entire VTU which is cryogenic facility. Does it mean that the world is moving without cryogenics? The world is there. Aerospace is there, aerospace needs cryogenics, electronics. But VTU is going on and everything is going on. And the only space where you get cryogenics someplace in ISC, some ICER, there's not so much fun. It's a very big building. Why should be a big building? It should be bread and butter, right? So that gap, what VTU is trying to fulfill through the center of excellence. Am I making sense? And that's also part of this biology. Okay, so squid, what is squid? Nothing. But if I tell you in a very simple way, what's the big deal? Then I'll tell you why we cannot build this squid. Why we are buying the squid for 4 crores. But we feel that if we get the support, we can build it for less than 20 lakhs. 4 crores versus 20 lakhs. Keep those numbers in mind. Okay? Circular ring, right? 2 Josephson junctions. Imagine a ring punctured by 2 Josephson junctions. What is a Josephson junction? Those are 2 superconductor regions separated by an insulating region. You are putting inside a metallic plate and putting in the middle of a magnetic field. My claim is this simple, humble looking device is so sensitive to magnetic field that it can pick up a fluctuation in magnetic field of the order of 10 to the power minus 21 Tesla. That's like the amplitude of the signals in your brain. Okay, when your thought flickers from one part to another part, there's some amplitude, something happens in your brain, right? That amplitude is 10 to the power is more than 10 to the power, probably 10 to the power minus 16 Tesla. Right? This humble looking thing that I told you in this one word, no, can pick up 10 to the power minus 21 Tesla. This apex quantum technology. And we can do it. Okay, now you are wondering, then why the hell we can? It's just a bloody ring, right? Okay. Problem is that ring, the size of the ring is few microns. And the size of the Josephson junction that you're putting inside, no, few nanometers. I ask you the question, do we have the technology? The answer is no. Because it is nanolithography. Now, is nanolithography so difficult that we don't know? The answer is simple. Just we didn't prioritize it. We never thought it's important. So, I'll end my motivation at this point. Lot more must to tell. I put some things here about how squids work, not required. Let me just, the last line I will highlight is so important. They can achieve spin sensitivity as low as few spins. Like few spins, but imagine 2 or 3 spins in the spin system is flipping from upstate to downstate. This technology is so crazy sensitive, it will pick up that spin flip. Okay, so now again I'm getting a little bit into bio applications. Squids are used many places, but now the new thing that has emerged are called nano squids. So you have this macroscopic squids, and now we are talking nano squids. From micron scale, we are going to nano scale. So that is another next level technology. And it is the moment, always remember that when you miniaturize any application or device, the first thing that a chemist or a physicist or an engineer will think, how can I use it for biological applications? Because biology needs this breakthroughs, right? We need this cutting edge technology. Okay, so you can do a lot of non-destructive testing using squids. You have heard of non-destructive testing, right? Anybody who has coming from an engineering background or an industrial background, you probably have heard the word NDT, non-destructive testing. You have an apparatus, something is working for you. You want to test without destroying the material, whether it's working or not, whether there's some crack in that car. So how do you test the stability of car? Actually, any top company, let me talk of cars. Cars is not a quantum, it's a very big macroscope. But as you know, it has something called a crash test, right? A car is banged against a wall or some moving target, and how many such hits it can tolerate. Randomly, one car is left, and it will be literally banged against the wall, okay? You see, so passenger sitting inside will survive. There's so many things that are done. You may have seen some YouTube videos also. But this is brutal technology, right? You're literally picking up a car and smashing it against something. Can you do the same thing smarter? By not, some internal crack is there, that crack will propagate. Can you detect those cracks or something without like hitting it with some hammer or some hitting it against a wall? That would be non-destructive technology, right? It's a very hot area, important area, particularly in mechanical and industrial engineering and things like that. So in any such subtle level testing, quantum technology boosts because you can really pick up. Okay, so you can do microscopy. This is actually called magnetic microscopy. Basically, you're imaging something with the help of squids, like supermagnetic quantum interference devices. And this is again another hot area, but okay. You can just, some of these names that I'm writing, you can just write down those names because, like, I please request you to go and find out how much these devices cost. That much you can do, right? I'm not asking you to study the physics of these things, and no. Just go to Google, try to find out a price tag for some of these things, and then you'll understand what is the National Quantum Mission trying to achieve, right? Suppose something which is costing 10 crores, you can build it for 10 lakhs. That much money you're saving for the country, right? So it's a top priority mission. All the things that I'm showing is different part on the plate, part of the meaning of National Quantum Mission. And then how much time do you have? You have 5 minutes? 5 minutes is there? Okay, so I will not show some of the slides on quantum LEDs and all this stuff. Because again, a lot of applications in what is called phototherapy. Have you heard of phototherapy? Curing with light? Anybody? No? So it's a very hot area.
They do for dogs. I heard they're doing for dogs. Loading. No, light therapy. Light, aroma.
And then you shine light, the light excites and nothing happens. It's a beautiful picture, very sophisticated, and that entire thing of phototherapy can be triggered by what are called as quantum dot devices and quantum LEDs. I'll skip this slide. So again, again, optoelectronics is a very hot area. The basic level optoelectronics is something like when you walk into a shop or metro, the door opens, airport, you just walk in, turn on the door. That's basic optoelectronics. How it works? Nothing. You come, some camera is trained at you, it blocks, you block the light, okay, and that tells a person has come. So door has to be opened. It triggers, that optics triggers some mechanics or some electronic component and the door opens for you. That is a gross level of electronics for you. You can just extrapolate now, start thinking, and it goes without saying that optoelectronics are very important when you're in therapy also, particularly biological applications are very, very strong. Okay, there are some 4 generations of quantum entities. I put some slide here, but I'll skip this. This is called external quantum efficiency. So if you ask me the question, sir, you're talking about quantum dots for the last so many minutes, what is it that you measure? So I will just give you one take-home message. You can just take this. It's called external quantum efficiency. So you can build something, but the first thing you have to measure is this quantum efficiency. So quantum efficiency is how sensitive it is to light and how much that desirable photon or whatever is an important part for you, it is emitting per unit signal. Like, let's output is to input ratio. Let us call that very broadly. The higher this output to input ratio, higher is the quantum efficiency. Am I making sense? So there are 4 generations through which it has gone through. It's like historical in nature. I'll skip this slide. Not important. Photomedicine, I'll skip. All these things I'll skip. Okay, so just 2 minutes I'll take on quantum tunneling based devices. As you know, quantum tunneling is another insane quantum feature where a particle which is trapped in a well, suppose I am trapped in a room whose wall is this high and I don't know how to do high jump. I'm an Olympic gold medalist in high jump. I'm a normal person. So there's no way I can jump over the wall and go outside, right? But if I'm a quantum particle, I can access part of me. But this, I know this sounds crazy. Like, let's say 10% of me can exist outside. 90% of me will be still confined within this wall. But 10% of me can go outside and explore. That's called quantum tunneling. And the way it happens is through Heisenberg's uncertainty principle. Delta E, delta T greater than H cross. So what's the idea? Suppose I have some energy. My energy is here. The wall height is there. My energy being lowered, I cannot go over the wall classically. But this energy is not fixed energy. In quantum mechanics, everything is fluctuating, right? Delta E is the uncertainty in energy. Remember? So what if this uncertainty energy becomes so high that actual energy goes above the energy of the wall? That possibility is there, right? So if that possibility is true, in the fleeting second, it's not even a second, it's like a 10 to the power minus 15 seconds or something. Actually, in quantum physics, there's something called a virtual process, which happens so fast that it's like saying, like let's say my friend Rajesh is sitting here, but actually he's not sitting here. He's sitting in, part of him sitting in his classroom, part of him sitting at home, part of him sitting in California. He's exploring the entire universe. In quantum, that possibility exists. I know this sounds crazy, but I'm not spending too much of time on it. So all these things exist. And particularly for this tunneling thing, let's imagine energy goes very high, delta E becomes very high. So some of the element can jump outside. So that's why I use the word, let's say 5% of myself can exist outside. Okay? Remaining 95% is still inside. So this is some very important technology because in many of the applications, quantum tunneling can enable that application to take it to the next level. So I have some list of items here, particularly these NEMS devices, nano electromechanical devices. Quantum tunneling is very important. One of the important technologies that you may have heard is called scanning tunneling microscope, STM. Right? Scanning tunneling microscope is also built on tunneling for now. Okay, I will now get into the design and fabrication. This is something that we are into. And okay, fine, I'll skip this slide also. Now I'll just last 2 minutes or 3 minutes on photonic integrated circuits. Those who are saying photonic integrated circuits are very important because they use photons instead of electrons for data transmission, processing, sensing, and so on and so forth. Again, 2D quantum materials, I'll just list a few. Graphene, very important. Transition material, dichalcogenides, they are called TMDs. There are a whole bunch of materials which are very, very important. And then we have something called the hexagonal boron nitride. Then we have something called the topological insulators. They're extremely important because they have protected edge states. So imagine the scenario where the edge is so protected that you can mess up with the bulk. That's like, suppose Nepal, it's a very bad example to take, but that's what's coming to my mind. Nepal is totally in a state of turmoil, right? They're building burning presidential palace, burning the parliament, right? So the bulk is totally in turmoil. You have disordered the bulk, but the surface is protected. So imagine the Nepal's border districts with India and China, everything's smooth, hunky-dory, everything's fine, economy is prospering. It's a crazy thing to think about, but turns out that you can engineer such materials and chemists do it routinely in their labs. They've got topological insulators. And they're so important, I cannot overemphasize how important they are. It's a very hot area. And it is used for, actually zero loss waveguides. Practically the loss, imagine an optical fiber where the loss is almost like zero. Can you understand how important that is? So these sort of things you can build with topology. Then again you have quantum dots, my Google quantum dots. Okay, so you have superconductors. Superconductors, anybody has heard of superconductors? Superconductors. Hello? None of you are superconductors. Only one boy is using his hand. Okay, tell me, what is a superconductor?
Sir, in cold temperatures it can...
Cold means how cold?
Around minus 273.
Minus 273?
No.
No, it doesn't matter. Tell me, at cold temperatures?
It has magnetic properties in the what?
Superconductor, what the word means? Forget about
With zero,
the resistance
without resistance, it can.
It's called perpetual current or dissipationless current. The way this experiment is done, you turn on a current by applying an external bias, by keeping the temperature of the material above the transition point, above TC. Let's say TC is 14 Kelvin for niobium nitride, whose transition point is 14 Kelvin. You have a helium cryostat, and you keep the temperature 100 Kelvin, or let's say your room temperature, 300 Kelvin, maximum temperature. Then you start lowering the cryostat. The moment it goes below 14, it turns superconducting. Now you turn off the external bias, the battery. The whatever current was generated, if you didn't lower the temperature below TC, it would be a normal metal or normal material. The current would die down immediately, right? Within a few microseconds, the current dies down. But now the temperature has gone below TC, so it becomes superconductor. So guess what will happen? That current will keep on flowing for, let's say, 14 days or 1 month, depending on how you engineered it. It's called dissipationless current. It keeps on flowing. So that's called superconductor, because the resistance actually crashed to zero. It has got tremendous applications. So it is so important that I could have easily spoken for 1 hour on that itself. The materials related to super, but I've just put one point number 5, superconductor. And some of these things are very important. Niobium nitride I put right at the beginning because in RBC we are fabricating this niobium nitride chemical, and this on the VTU venue also. And I request many of you to actively look at these materials also. That's my humble request. Okay, and there are nonlinear materials as well as again we are building those materials. Nonlinear optical methods are optical crystals are very important. As I remember beginning I told one photon splits into two. What is that crystal? It's a nonlinear optical crystal, another crystal. If you buy that crystal, you can check out. I'm telling you a name, at least that much you do. You type on Google, BBO crystal. Imagine you have lots of money, you want to buy a BBO crystal. Find out how much it will cost you. And I am telling you that if I build that crystal in RBC or anywhere in CMR, let's say, I can build it for 5,000 rupees. But so far, somehow, yeah, that's why I said we woke up a little bit late. But let's move it now. Nonlinear materials are extremely important for quantum optics and quantum applications. I cannot overemphasize as a whole. It's just written under point 6. But it's just too much. It's so important. This was quantum emitters and quantum detectors and lithium memory. Actually, this crystal, which I put is the crystal that we're trying to grow right now. For that, we want to build one apparatus. I just tell you to do it because I'm interested myself. The point is, that apparatus, we go to the market and want to, that crystal growth, it is available. It costs only 28 lakhs. But when we thought about it, we got on to design and all that. So then we figured out we can do it. It's like, I'm not going to bore you with the details of how to build it. It's nothing. And we can easily build it for 4 to 5 lakhs. As a matter of fact, recently I asked for funding. In the third round when I went, no, the funding agency actually asked me, what is your innovation? What is the innovation here? I said, zero innovation is there. Then what? What are you doing? I said, nothing. I'm just trying to reduce the price. Something which is 28 lakhs or 24 lakhs, I'm trying to do it for 4 lakhs. He was not able to answer. You will get a paper out of this? No, I will not get paper also. You will get a patent? No, I don't think I'll get a patent also. So then how is it possible? You are not believing. So tell me, what is the new thing that you have done? There's nothing new. Then why your price is coming down so much? I thought for 2 minutes, and I'm not kidding you. I'm 100% being honest here. So I told that I actually have not figured out why is their price so high. I could not figure out. So somehow he was not convinced. Let's see, if I get the money, I will see. I still not that decision not been taken. But I have to be honest, I have to be truthful. There's no, just that these technologies are so sensitive and so apex technology, you know, and there are no players in India. Everything is priced extremely high. But if you think as an engineer and get into this area, and I strongly request you all of you to think in this way, right? Get into these areas and everything will change for the better. Okay, so I think I will stop. No, some want to know, I will stop. Thank you. So, thanks.